I want to start this talk. This is going to be a fairly technical talk. I'm gonna go into some math, at least at it. It's going to be a technical talk, not because I'm going to go into great detail, but because I'm going to go over a lot of things in maybe not as much time as they deserve. But I'm going to start with a little bit of motivation, which is why do we care about this? Why do we care about having a principled approach to structured data? Well, something that I've sort of found out the hard way over the last 2-3 years in trying to do things within Algebraic Julia is that we have a lot of really great. Okay. Oh, also, we're on a Zoom, right? Yeah. Okay, good. Because Dana wanted us to be on Zoom. Okay. Anyways. So why? So what have I learned over the last 2 or 3 years? Well, there's a lot of really cool stuff that we can do with models using the sort of principles of Algebraic Julia and the principles of compositional modeling. Specifically, well, we have like formal semantics for graphical models. And so with semigrams, we can draw a model graphically, and then have that model be actually, something that you can execute, something that you can work on. There's also lots of cool stuff that is not totally finished, but sort of in the works, about building models interactively. Perhaps via like, applying rewrites to things, or via like combinatorial search. And also, we also in ASCIM, we want to have archives of models. And so like a database of models that we can search not just by tags and metadata for the models, but also by like formal properties of the models. So, I want a petri net that has a susceptible population and an infected population. Give me all of the petri nets in the database that have this property. But when we're manipulating models graphically, interactively in a database, then suddenly a basic assumption behind almost all of scientific computing is violated. Namely, the assumption is text files in version control are our source of truth. Now, notice that this is not incompatible with structured models in general. Like, one of Algebraic Julia's philosophies is that, your model shouldn't be arbitrary code. Your model should have some structure, and that's not incompatible with text files in version control being the source of truth, because we can just say, oh, okay, write all your models in a DSL, a domain-specific language, and then that's your source of truth. Why does that work? Why does writing models in a DSL and and just putting those files in version control. Why does that make sense? Well, it's because generally formats that are written for humans to write assume that edits to a model don't drastically, like a small edit should lead to a small line-by-line edit. And this just makes it work well with Git. Like if your edits are local, small, if they're things that can be accomplished by a text editor, then they'll probably be diffed well by Git. As a contrast, if you're editing something graphically, if you're editing something interactively, some interactive change that you do to a model might be a small semantic change, but if you're storing this on the disk with JSON, suddenly your small semantic change might totally like shift everything in a way that, like, first of all, makes a big Git diff for something that's a small, like fundamentally a small change. And secondly, if two people make two different changes at a high level semantic, at a high semantic level, via, say, I'm just drawing a wiring diagram in semigrams, you're drawing a wiring diagram in semigrams, and now we've made two different changes. Now I push to the repository, you try to push to the repository, you get a conflict. Okay, I'm gonna fix this conflict. Oh, now I have this diff of these JSON files that I have I didn't write these JSON files. Where did these JSON files come from? Are you gonna expect me to like semantically to figure out like the low-level structure of the protocol that you didn't write this at all, you just edited something in Git. So these, like, graphical, interactive, and database, the affordances to work with models in this way are somehow, I think that this is fundamentally at odds with the assumption that text files in version control are our source of truth. So that's fine. Why do we need this? Why do we want text files in version control to be our source of truth? Well, sort of because version control is really nice. There's a reason why every single software development shop from 2 decades ago to now uses version control instead of Dropbox for their source. It's because version control gives, first of all, transparency into dev process. When you have version control, you can see how things have changed. If something messes up, you can figure out what caused that. But more importantly, this gives accountability. If we had all of our code in Dropbox and I decided to be sneaky, I decided to change one line of a file, it would be, first of all, like just me being able to mutate that by default and then it going into production or something. Like that would be terrible. Second of all, it's not clear who did that. If you don't want people able to sneak things in. And third of all, like, version control means that you get to do collaborative decision making for what changes get accepted. which is really important. Like if you think about like, what is the workflow of version control? Well, you have one collaborator, he or she writes some changes. They submit the changes, and then everyone on the team, if they so choose, has an opportunity to look at the changes before they're accepted. And there are some other features that are really nice about version control. One, version control is sort of immutable. You can make a change and then you can undo that change, but that's different than just like undoing that change. You get to see, oh, I made that change, then I went back. And you always get to, you never get to change someone else's stuff. You can only add things. If someone else is like, no, I like the old way better, they can still do that. So version control is great. And so this is why, I think that this is part of the reason why there have been lots of attempts to do something like, graphical editing or like graphical programming languages. Or even, this is sort of a less extreme example, but there's a program that Evan and I and some other people here like a lot called TechMax, which is like a WYSIWYG software for scientific documents. And it has a text format which corresponds sort of to how things look at the screen. So it's not horrible to do manual get conflict resolution there, but it's a little scary. I don't really want some text that I didn't write. I don't want to have to conflict resolve on. So I think that sort of the security and the sense of security that you get from version control, and the fact that like things that are outside the domain of version control, things that are not just editing text, is not compatible with that. I think that's really has prevented us from moving beyond text. Yeah, shall we?
I have a comment that another big reason is preventing dependency hell, right? So you could have different branches for different versions, and then you can manage dependencies a lot easier if you have version control. That's one big reason for that. I have a question. So,
yeah.
So you say that it's really hard to archive models, and that's at odds with this assumption that text files are in version control. What if we invented the right DSL, which then made this assumption correct again? So you said that like we had a semagrams, we made some small changes in semagrams, and made this huge change in the JSON. But what that basically either means that somehow version control is wrong for semagrams, or semagrams is stored in somehow the wrong DSL. And in the right DSL, then you get back this version control. I assume you're going to say that basically if you go down this route, we are going to end up with what you are going to describe.
Well, so it's an interesting question. I think the answer is not that text is intrinsically bad. The answer is that not every like conflict model fits well into line by line diffs.
Okay,
I think that's the fundamental reason. Yeah.
And I think it can be simple enough to give an example. Like you could just use like an interchange law type argument and show that. So like if you put for, you do me wrong.
Oh, sure. Yeah.
Test and G composed with H tends to K, right? Like you have to make a choice about how to linearize that, and you can make a marginal change, semantic change in one of the, in that diagram. That no matter what choice you make for linearizing into text, you can induce a large change in the text.
Yeah.
I like that.
So just the structure of text, and not every expression semantically has a linear flavor. One-dimensional flavor.
Practical examples if you've ever had the diff Jupyter notebooks. Like,
Yeah, that's another great example.
Okay.
Jose?
Yeah, I was gonna. Oh, yeah, maybe, sure. Thank you. Maybe remark that, like, what it sounds to me like the problem isn't necessarily text in terms of it being linearizable or not. It's almost, I think the thing that causes chaos is you have something that actually represents what you want to diff, and then you have something that is generated. We don't diff binary files.
Right.
Because you compile your C code, and you don't diff the executable. The same way you want to diff the graph, you want to diff whatever your thing is. The JSON is just what we use to store it, and
Right.
unfortunately, it seems like that is generated in a way that is just not amenable to. But obviously, it is somehow representable, and it should be diffable. So I'm interested in how.
Right. You want to diff your source of truth. You don't want to diff the artifact of your source of truth. So if text files are your source of truth, which is great. I mean, I love text files. That works for a lot of things. Then it's fine to diff text files as your source of truth. But the assumption, but there are things that we want to build that break the assumption that text files are our source of truth. Yeah. Okay. So that's the motivation for all of this, where it's like, okay, we have to break free of this text file model. Now, so what do we go to? Well, the nice thing about text is that it's extremely canonical. There's sort of one idea of what is text. Once you move away from that, there's a million choices to make. So it's not really just building like one new system. It's how can we build a system so that you can define some structured data and then be able to work with it via version control. And let's talk about some things. Let's talk about some concepts that you would want to do for, like, how do you build up structured data? Well, we have algebraic data types. So we want to be able to, okay. First of all, primitives. Got to start from the beginning. String int. Now, on top of that, we want records. So, i.e., products. Some types. So this is basically the feature set of protobuf. Or basically, this is like the feature set of like protobuf and every other serialization format out there. And that's great. But why do I think that this is not quite enough? Well, we said that we wanted to move beyond text. And Brendan gave the great example of like, why do we want to move beyond text? Well, text is like sort of intrinsically linear. And I claim that this stuff is also sort of intrinsically linear. We're putting a structure on things. We're like, things of this form, records, some types, blah, 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 blah. Your data is roughly a tree. It maps very well onto JSON, actually. So if we were just doing this, there's not much point to it. And another reason, but this is sort of a more pragmatic reason, well, we love acsets, and acsets don't fit into this. So what's sort of the one weird trick that we can add to these features to get acsets and to get other things? Sorry, I'm just going to take off my sweater. And now we're getting into the technical part. Sigma types over the night sets. Okay, this seems like it's sort of out of left field, but I want to convince you that once you add this, a lot of things that you cared about are now expressible. So so first of all, what is this? Well, I'm gonna give an example for discrete dynamical systems. So DDS. It's a sigma type, so I have this big sigma. X is a finite set, and then I have a function x to x. Now, this looks kind of like scary dependent types. But I actually haven't done anything that is not like just normal data. You can think about this as like, what is x? Well, really in practice in an implementation, x would be like a list of UUIDs. And then this function from x to x would be like a hash map of UUID to UUID. UUID is like just a random 128-bit string. They're useful because you can just generate them randomly, and they're probably nobody will have ever generated that specific one before and ever will again. So that's a good. Yeah. So anyways, so this looks like a scary dependent type, but it's actually still quite serializable. And so I claim that in general, like a type theory built out of primitives, records, sum types, this sigma type functions. So this is a function, but it's only out of a finite type. I only allow a function out of a finite type. And the reason why, and a function out of a finite type can just be serialized by listing out, like, this element goes to this element goes to this. It's fine because it's finite. So I claim that a type theory that only has these type formers, primitives, records, sum types, sigma types, finite functions, or functions out of finite types. Any type that you build up recursively out of these formers is serializable. And this allows us to do something that we couldn't before. This allows us to sort of well-type references. So for instance, let's do graphs. This would look like E equals fin, V equals fin, E to V times E to V, which is sort of edges, vertices, source, target. So in general, these allow you to make data structures where bits of that data structure can refer to other bits of that data structure. So notice that, like, this V is the same here and here. So let me give you some more examples of such data structures, if I can turn this on. Okay, so I like to call these combinatorial data structures. It's a data structure where parts of the data structure refer to other parts of the data structure, possibly in a cyclic manner. So we have cyclicity here, where a discrete dynamical system, there could be a loop that goes around. And some examples of this are wikis. Wikis are of this structure. In a wiki, you have a set of pages. Each page has a set of links, and each link points to a page. SQL also has this structure. In SQL, you have a bunch of tables, and the tables can have data, but the tables can also point to rows in other tables. A doubly linked list is also of this structure. It's sort of a funny example because most people think of this as an implementation detail rather than like part of the abstract definition of what a list is. But you know, implementation is interesting too. Another example is an abstract binding tree, as these were invented, or I think Fiore invented them. There may have been abstract binding, but at least he did a lot of work on them. And the idea here is instead of like, you know, it's very traditional in, say, compilers written in Haskell or whatever to express your syntax tree as an algebraic data type via records and sums, and then your variables are like text or integers if you're doing De Bruijn indices. But actually being able to type, say, to give in your data type, oh, every time I have a variable, that should actually be a valid reference to an earlier binder. That's like a data structure that refers to itself. And then finally, and this is sort of the big fish of where I hoped this to go, is nested wiring diagrams, where this partly has like a tree structure. The tree structure is like each wiring diagram has boxes, and inside that box you could put a primitive system, or you could put a whole other wiring diagram. But they're all sort of interconnected, and in sort of in a non-trivial way, in that the inner ports, the ports on the box here, become the outer ports of the wiring diagram inside that inside that box. And in order to like well type that, you need to use like these sigma types over. I mean, you don't need to, but that's one way of doing it that I've found. Okay, so I'm not gonna get too into like the specifics of how to do all that stuff. I'm gonna start talking about the categorical semantics, some ideas I've had towards the categorical semantics of how to actually interpret a type theory like this.
So the examples are great. Can you just, why have you chosen the word well-typed reference as this capability? What is,
so
the reference is the functionness, and then the well-typed is what?
yeah, so the idea is like, you know, I could model it a graph instead as like a record. E int v int source array int target array int. And this sort of expresses the same data as this. I have like two finite sets. I mean, here I've chosen that I'm going to represent the finite sets as an integer rather than as a set of UUIDs. That's not important. And then source is just like says, okay, for each, there's sort of an implicit guarantee here. You might write this as a comment in the data structure that, oh, the length of source should be E, and each element of source should be between 1 and V. but I can't actually put that in the type. So the ability to have these actual finite types allows me to make sure that when I reference a v here, when I have an implicit guarantee that each integer here refers to a vertex, I can actually put that in my type rather than having that be something sort of implicit.
So on this list of like features of this like I don't know serialization for this like this data format, do function types?
Oh yeah, I should also put.
Somewhere, and what is the difference between sum type and a sigma type?
Sum type is like a finite sum.
Finite sum, okay.
Yeah. Functions out of fin types. Yeah. Yeah, and notice actually something kind of neat about this is that I automatically get like a tensor library for free, because I can say like, oh, what is a matrix? Well, it's just a function from like v squared to float. So that's kind of cool. So yeah, so let's get into the math. We've been talking about type theory, blah, 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 blah. So in, I think in 2000, John Baez and Dolan, James Dolan, they published a paper coining the term stuff type. And for them, a stuff type is a functor. For them, a stuff type is a groupoid. Let's say G in groupoid, along with a morphism G to fin, the groupoid of finite sets. And so this is a generalization of combinatorial species, which classically are functors from fin, the core of finite sets, to set. And these have been used all over the place to describe combinatorial structures. And the idea is that a combinatorial, like, for instance, you could have a functor like this for simple graphs, which sent a finite set to the set of simple graphs with that set of vertices. And then there's an action, there's a groupoidal action there. The reason why we have the, we only have isos here is that there are a lot of combinatorial structures which are not functorial in general morphisms. And so when you take the Grothendieck construction of a functor from fin set and isos to set, you get a groupoid sitting over fin. But you get a special type of groupoid. You get like a fibration. So the innovation of Baez and Dolan was to say, okay, what if it wasn't a fibration? What if in fact it was just a general morphism? And for instance, one example of this would be the functor from a graph, which is like all graphs, so directed multigraphs, to fin, which sends G maps to now, okay, I'm using G in the same place, but whatever, to G of V. And we can say graphs with graph isomorphisms. Now the fiber of this is a non-trivial groupoid. It's not just a set. And now because of some facts about groupoid. It turns out that the Grothendieck deconstruction for groupoid says that functor, like a groupoid along with the functor into fin iso, that's actually the same thing as just a functor from fin iso to groupoid. So for instance, for graphs, this would send a finite set to the groupoid of graphs with that underlying vertex set. Now, why stop here? Why just have one finite set here? Why not think about sort of combinatorial types that are parameterized on two finite sets? Yeah, what's up?
So I have never once thought about the groupoid of graphs or finite graphs. Why is this? So this is an example of a stuff type that is not a combinatorial species.
Mm-hmm.
Why do I want this example?
Well, we love graphs, right?
But I like the category graphs, not the groupoid of graphs.
Ah, yeah. So that's a good point. So where's my nice category structure? Well, what I said at the beginning was that there's lots of things that sort of don't fit in, that aren't functorial in general morphisms. And one thing that in my experience in algebraic Julia is that we model a lot of things as C-sets, but or acsets, but like the acshet morphisms or C-set morphisms are not actually the natural morphisms of those things. So this is sort of the reason why I'm just doing groupoids here is that there may be more morphisms, but I want to be sort of minimal. I'm thinking of this as foundational, and I want to capture the fact that like when you, well, okay, I'm skipping ahead a little bit, but like when you take a sigma type over finite type, there's always a natural groupoid here, but there may not be a natural category.
So in particular, then I'm interested in like properties of my object that I want to find up to isomorphism and not up to general notions of morphism.
Yeah. For instance, here's an example of this. Like when we do petri nets, whole grain petri nets, when you write it out as a C-set, the natural notion of morphism just for C-sets allows you to collapse arcs. So you don't have to, you can send a transition to a transition with a different number of inputs and outputs. And what you actually want to consider is the automorphisms. But that's sort of, that is based on like your understanding of these things as like how you want to use them. It's not sort of based on their intrinsic definition. Yeah, what's that?
So another question is like, so you motivated the move to stuff types by observing that for multigraphs, you've got this edge set as well. Seems like a smaller change you could make would just be to have some sort of like multiply typed kind of combinatorial species where you have like the core fin set squared to set that sends like a pair of sets, the vertex and the edge set to set. Is that adequate for your examples, or do you need some greater degree of generality than something like that would be?
I do, and I'll get to exactly why.
Yeah.
So, yeah. So okay. So we're moving, from just one thing here to multiple arguments. And what I want to think about, I want to think about this as like a context. In the sense of type theory. Like I have a context where I have some like finite types in my context. And what can I do with the finite types in my context? Well, I can take sigma types over one of the variables in my context. And that's where we need this to be a groupoid. Because you're right, I have like graph is like fin squared to set. But now I essentially take the Grothin deconstruction with respect to one of the variables, and I get something from fin to groupoid. So in general, like, we're going to end up in groupoid.
Okay, so you just want to have everything be in that world from the beginning.
Yeah. And what this would look like is like E fin V fin derives like, E to V squared is a type. V fin derives sigma over E fin E to V squared. It's a type. So this is sort of a way that I can write down I can use the type theory just based on these operations to write down this stuff type. So the advantage of, even if we only really care about univariate stuff types, the advantage of going to multivariate stuff types is often it's natural to describe a univariate stuff type via like a sigma type over a multivariate stuff type. And via this construction, I can, yeah, what's up?
What's the rule you use to go from, like, how did you infer the one below the line from the above?
So this is just like the formation rule for sigma types. Like I'm assuming that in my type theory I can do stuff like this. But like if this were just like type, then this would just be standard Martin-Löf type theory. The difference is that I like restrict myself to only taking sigma types over the universe of finite types. And via this whole construction, I can build the group, like any acshet schema, I can build the groupoid of acsets on that schema. So specifically as a nullary stuff type, which is just a groupoid. I take the multivariate stuff type with all of my object types in the context, and then I have like all of my columns just as finite functions, and then I just sigma over all of my object types. And now we can go one step further, which is so if a multivariate stuff type was a functor like this, we can talk about or like to groupoid, fin n to groupoid. A generic multivariate stuff type is a functor from groupoid to the m times fin to the n to groupoid. And this allows me to, if you think about fin iso, if you think about like multivariate stuff types as being sort of generic over fin type variables, this allows me to be generic over both like type variables and fin type variables. So this recovers the ability of acsets. Like when I write down in Julia, when I write down the schema for a weighted graph, what I get out is a Julia type that's generic over the type of weights. So this allows me to also express generic types.
Are there attribute types that will be non-trivial groupoids?
Possibly. For instance, say you want, here's an example of an attribute type, graphs again.
Okay.
So we could have graphs, weighted by graphs. Why not? The nice thing about this type theoretic approach, as opposed to the sort of like just one and done schemas, is that you can just sort of build these things up as far as you want. So basically, I claim that sort of, developing this type theory and then developing the semantics for it as multivariate stuff types gives us a good theory of data that allows us to well type pretty much anything that we might want to serialize. So so I have 10 minutes left. I want to talk briefly about version control, which is a little bit orthogonal to all of this. So I'm just going to erase all of that. So version control. The idea behind version control is that so version control is, I wrote down a specific phrase that I like. The goal of version control is accounting for the collaborative creation process. I'm sad that David Spivak isn't here because I kind of wrote that line for him. But the important thing is that when you make a change, you want to account for that change having been made. So the first step in formalizing version control is to ask yourself, okay, well, what is a change? And the simplest thing, maybe simplest thing for a category theorist would be to say, okay, here's a notion of change that makes sense. We have a category where we think of the objects in the category as values, and then a morphism is an edit that goes from the state, the value before the edit, to the value after the edit. So I call this a value edit category. And value edit category is a definition is a definition with an attitude. This is just a normal category, but you think of it as the objects are values and the edits are, and the morphisms are edits. But now the thing about this, so we could say, well, all right, now what is the state of my repository? It could be like initial state, terminal state. So it could just be like, and then I say, well, and then the history of this is incorporated in this like one big edit. But this is not really satisfying because this means that we no longer have a sense of like, if we try to stuff all of this in the category, then we don't have a sense of like, when does an edit actually undo a different edit? Because like if we want to actually store how like the history, then this ends up having to be something like a free category. And then the compositional structure of edits is not interesting. So instead, I want to say that a history, well, okay, so here's another possible definition for a history. Another possible definition for a history is that we could say, well, we have the interval. Well, okay, that's maybe not. I'm going to say I sub n. This is like the linear order on n steps. And so we could say that a history is a functor from the linear order on n steps into C. And this is essentially blockchain.
That's just a path of length n.
It's just a path of length n. And this is how like Git works, you know, like the history of a single, of a branch is just, one of these linear orders. But this doesn't actually accurately represent the history. because sort of when two collaborators are working in parallel, there isn't necessarily a linear order between their changes. So really what I want to say is that a history is just an arbitrary finite poset P along with a functor from that finite poset into C. And the relation between points in this poset are just, the idea is that one point is after another point, or is greater than another point if like the previous point is in the future point's like past light cone. If like the changes introduced at this point.
If they're eventually merged.
No. If like when I sort of minted, like really the points in here are like commits. And it's like when I made this commit, did I observe this previous commit? And one sort of interesting consequence of this being a poset and requiring this to be functorial is that whenever I have a diagram like this in the poset, then it has to be sent to a commuting diagram here. And so that has the requirement when I make a new change that depends on these changes, then I have to reconcile the diverging changes from these two commits in a confluent way, so that the edit history here is the same as the edit history here. And yeah, that's sort of the intuition here. Notice like one way of doing this would be to create a push out. And like depending on what I'm version controlling, okay, yeah, almost out of time, that might be a reasonable thing to do. But I might be version controlling something, like say I'm just version controlling an integer, right? There's might not be a natural notion of push out for changes of the integer, and if the category of edits is just the discrete category, then really all that is happening here is that when I do this, you know, the person who makes this commit has to choose. So anyways, I want to sort of take this perspective on version control as the point of the version control system is not to tell you how to resolve the commits, it's to account for how you choose to resolve the commits. And I'm just going to say one more thing really quick, which is that what I hope to do is I hope to sort of build, like there's semantics in groupoids for this type of theory, but I also hope to build semantics in value edits, where basically, you know, when you have a sigma over a finite type, then an edit can be like removing or adding things from that finite type. And then I have some exciting things about like, well, if you consider the category of the where an object is like the category of things into here, then that's actually a pre-sheaf on this poset. Things get exciting. Anyways, I'm not going to go into that. I think I'm going to finish there.
Thanks, our speaker. And any questions? It might come with a mic. We'll try this out. Good luck.
Thanks, Owen. Nice talk. So one question I have is you've mentioned a couple times that a lot of combinatorial data structures don't come maybe with a notion of morphism that's more flexible than some kind of isomorphism. But presumably in this category of edits, we need to have more morphisms than that. And so do you have a way of generating what those morphisms should be from like the descriptions of these formers and stuff? Or?
Yeah. So, no, I have some ideas. Though.
Okay.
Notice that notice that the morphisms in the value edit category are going to be different than like morphisms of C sets that we know and love, because they're going to be more like spans of C sets, in that you can remove things and delete things, or maybe partial functions of C sets, or maybe injective spans. There are choices to make, and but there's in the Baez and Dolan paper on stuff types, there's a really interesting section where they generalize the annihilation and creation operators from quantum mechanics to work on stuff types. And basically those become operators on stuff types, which in my terminology would be bivariate stuff types. Which like sort of a matrix. If like a regular stuff type is like a vector, then it's a matrix. And actually the matrix multiplication can be done with this sigma operator. So I don't have a full understanding of how to turn that into value edit categories and version control, but that's sort of the path that I'm looking down into. Yeah.
Any other questions?
So, to summarize,
Take the mic.
sorry, I got it. So to summarize, stuff types give us semantics for like the most general notion, a very general notion of structured data. And then these value edit categories help you keep track of version control. What happened to the graphical sort of language aspect? So I can see that these data types. So you're saying that these data types are also rich enough to capture sort of graphical structures, and that's enough.
Yeah.
Like we don't need any special.
The sort of key affordance that you need for graphical languages is like cyclic references.
Okay.
And that's exactly what you get here, because like sort of this is a very classic problem in serialization, which is like, how do you serialize a cyclic data structure? Well, how do you store a cyclic data structure in memory? Well, you have pointers and it refers to each other. But in order for that to happen, you sort of need this global namespace of memory. Because, when you have things in memory, they can just point to each other willy-nilly in any cyclic thing. So, like, being able to bind a finite type operates like that, where now I can have things, and because this is sort of in global scope, anything here can just say, oh, I'm going to point to an X, without having it to be like, oh, the thing that I'm pointing to is part of my tree.
Concretely, is there a notion of a diff in this approach?
In here?
Somewhere here, right? We're doing version control, and diffs are how I understand how I keep track of version control.
Yeah, so that was Evan's question.
Okay.
I'm hoping to get some notion of a diff which basically says like, okay, so diffs for primitives are just discrete categories, the discrete value edit category. Diffs for records is just like a pair of diffs. Diffs for some types is either I stay in one thing and I have a diff, or I just like move over and I don't have any, like it's just like a total change. And then the tricky thing is diffs for sigma types. Diffs for sigma types should allow you to add and remove things from the sigma type. But then the question is, like, if I've added something to the sigma type, there isn't, like, that's not functorial. So I need to sort of add something to the finite type and then fix up what is here to make it compatible with this new thing. And figuring out how to like coherently make sense of this fixing up is the challenge. Yeah.
Thanks.
Thanks. All right, one more clapping. Yay! Thank you so much, Owen, and we'll